Today we are going to talk about how do you find the using calculus, how do we talk about arc length and surface area. So first we are going to start off with arc length and how is the formula derived, and then we'll talk about surface area. So when we talk in the sense of arc length, let's just say you have some kind of curve going on, and arc length does not mean the same thing as the area. You can relate to something when we found something on your previous classes, such as circumference, right? So that means only the outer region kind of thing. So we want to find out the length of the segment of a curve. So let's just say for derivation purpose, let's call it C, and let's call this right here as our D. This is our point A, and let's call it, this is our point B. And this is our function f of x. If I'm interested in finding this whole segment, right, from here to here, what we're going to do is we're going to take really small, tiny segments. So let's start off by just say, what if I created a little triangle here? And if I zoom in this triangle, how's that going to look like is something like this. And any changes in the x, right? So this is the change in x, we call it delta x. Any change in y, we call it delta y. And this is basically this right here. That's this right here. We can even get more tinier, but we're not going that tinier. So yes, it is. If I get more tiny, small, it's going to be the exactly looking like a triangle, as long as it's not a point. So by Pythagorean, you know, this makes a 90-degree angle. If I happen to call this as my L, this small little chunk, then by Pythagorean, we can say the length of this small piece can be written as, remember, c squared equals a squared plus b squared. So we're saying L squared equals square root of, or let's say L, because if I wanted to just solve for c, this c would be square root of a squared plus b squared. So our L in this case would be delta x, that quantity getting squared, plus delta y, that quantity getting squared, using Pythagorean. Moreover, now that's just only that little chunk, right? We want to find out all of this little chunk. So we are saying, I'm going to go ahead and start taking triangles. I'm going to make triangles, small triangles throughout that whole line segment. And when we say small triangles, and towards the end, I should really sum up from A through B. So what we're saying, when you say integral for the sum, this is really saying, this is nothing but saying this symbol is the Greek symbol called sigma, which stands for summation. I'm going to take small triangles from 1 through all the way to infinitely many I can take, n of square root delta x, that quantity getting squared, plus delta y, that quantity getting squared. And I'm also going to call it the ith component. Why am I saying ith component? Because I can have infinitely many triangles, right? I can have another one. So the first one, second one, third one. So I corresponds to the first. When I is 1, 2 would be the second one, and so on. Okay. Upon factoring out, if I happen to factor out a delta x from here, how's that going to look like? Or delta x squared from here? So we can write, this is nothing but saying summation from I equals 1 through n. If I factor out a delta x getting squared by brute force, like forcefully, if I can factor it out, then I would have 1 plus delta y getting squared. As I factored out forcefully delta, makes sense here, because this would give me delta x squared times delta y squared. How do I make it work is, as I forcefully factored this out, I also have to do it, divide it out, right? Think about this. If we have x squared plus y squared, and if I wanted to take out x squared, we're allowed to do so, then I have to put y squared over x squared. So that cancels out, it gets you back the original. So upon doing that, notice if you have a square root or a radical on both, upon factoring out a delta x, x squared, notice this is nothing but saying that's equivalent. If we split out the square root into this right here, which is the same thing as saying delta x, that whole quantity getting squared, so they can cancel out, leaving you out with nothing but delta x. So we can really write this as saying square root of 1 plus what is delta y over delta x? Well, we can write it like this, delta y over delta x, the whole quantity getting squared. And then this is, we said, square root and the square cancels out, so you have delta x. Now we can actually translate this problem. We're saying, hey, I'm going to find out the integral of all of this, or I really said the keyword. I'm going to find out little triangles, and I'm going to add up all of that. That's why summation. But summation is the same thing as it's an integral. So now I can say the L, which is the arc length of all of this segment, right, would be the integral from A through B. Here's my A, here's my B, A through B, square root of 1 plus, but if you notice, what is delta y over delta x? That is your really dy dx, or someone could have called it f of x. So this is really, or dy dx or f prime of x. So this is nothing but saying, this is the same thing as saying f prime of x, or dy dx, whichever you feel like, getting squared. Delta x is the same thing as dx. And this right here is the arc length formula derived. So you'd have to remember this. Notice that this is the arc length on the x, right? So you can have arc length in terms of y as well. There's going to be certain change in that case. So it would be, instead of saying a through b, you'd be saying c through d, because these bounds a and b are your x bounds here. But if you're doing in terms of y, so it would be c through d, right? So this would be your y bounds, square root of, instead of saying f prime of x, you'd say f prime of y. So you'd have 1 plus f prime of y, that whole quantity getting squared, then it would be dy, not a dx, because we're talking in the sense of y. So some people also, or some textbook writes it as dy dx. That's the same thing. Then you square that. This would be something as saying dx dy, right? So whichever you feel comfortable. Okay, let's look at an example. So here's our integral problem. Find the length of the function 3/2 x raised to the 2/3 from x equals 1 to x equals 4. Okay, so however the curve looks like, we want to find out the length of that curve from this region x equals 1 through x equals 4. So notice what we need on the arc length. I wanted to clarify something. This is not the second derivative. You're taking the first derivative and squaring it. It's not f double prime, so be aware of that. That's a typical student mistake. Okay, so let's go ahead and draw this. Well, you don't have to know how to draw this, but the idea, as if you're a pictorial person, I don't care what's really happening. I only care from 1 through 4. I want to find out the length of this guy right here. So what do I need? If you recall on the formula needs some kind of bounds, which we do have them, right? Integral, what are my bounds? 1 through 4. Then it says square root 1 plus, it says f prime of x, that whole quantity getting squared. Well, what is f prime of x? We need to know what is f prime of x. If my f of x is 3/2 x to the 2/3, my f prime of x would be 3/2. This 2/3 gonna sneak out in front, so 2/3 x to the 2/3 minus 1, right? So that would give you negative 2/3. This is gone, and dx, I should write it. So I would have that quantity as x to the negative, or this is negative 1/3, I squared it already. So f prime of x, if I square that, I would have x to the negative 1/3 getting squared. That would be x to the negative 2/3. So this is x to the negative 2/3. So I did all my side work here so that I don't make the problem complicated. Okay, now it might not look like we know how to solve this, but we do know how to solve this. So anytime you get stuck doing an integral problem, you probably want to clean up your algebra. So let's look at some of our algebra skills here. Calculus is pretty easy. The algebra part is maybe a little tedious. So let's see how would we clean up this algebra. So if we look at this problem, if I happen to have, let's do it here, 1 plus x to the negative 2/3, and I am kind of stuck here. So what we can do is, well, you have a radical, we can rewrite the negative exponent as a positive exponent, which yields us having something like this: square root of 1 plus 1 over x to the positive 2/3. We don't like negative exponents, so we can write it as a positive exponent. Now we can think about LCD. Imagine a 1 underneath here. So the LCD in this guy is x to the 2/3. With that being said, now we can actually work with the LCD, making the same LCD. So I would have x to the 2/3 plus 1 all over x to the 2/3. Now also notice on the property of radicals, if you have x over y, you're allowed to write square root of x and over square root of y. So if I have the square root on top and on the bottom, I'm allowed to write this as saying square root of x to the 2/3 plus 1 all over square root of x to the 2/3. And also recall, square root is nothing but saying this is the same thing as saying half exponent, 1/2 of an exponent. So this is nothing but saying this is 1/2, and x to the 2/3, this is 1/2. And if I happen to clean them up, these 2's are gone. I cannot clean the top up because of that plus 1 in there. So it really narrows it down. So the problem really melts down to something like this. So we have, I'll move in here. So we have arc length integral from 1 through 4. We have x to the 2/3 plus 1 raised to the 1/2 all over, you have x to the 1/3 dx. Okay, remember from last time we said we always want to try u sub first. So what would be our u? Probably u would be our inner function. So let's say if I happen to take my u as saying x to the 2/3 plus 1, what would be my du? My du would be 2/3 x to the 2/3 minus 1 is negative 1/3 dx, because the derivative of 1 is 0. And if I wanted to rewrite this, du is nothing but saying this is the same thing as saying 2/3 x to the positive 1/3 dx. Now notice something beautiful is happening. If you really think about this, x to the 1/3 is on the bottom, x to the 1/3 in the bottom. After this only happened after, because we cleaned up our algebra. Dx is on top, dx is on top. What are we missing is we're missing these 2/3. Well, that's not a problem because that is just a constant. So I'm going to go ahead and put a 2/3 here. How do I balance it out is as follows. I just put a 3/2 outside. So this is nothing but upon doing this substitution, this would really look like 3/2 integral. I'm not going to put my bounds in here because I'm going to write them because u equals x to the 2/3 plus 1. So this looks like u to the 1/2 du. And that's a super easy problem. You can say this is the same thing as saying 3/2. You're not wrong if you wanted to do a change of bounds by putting those x values 1 and 4 over here for u and put those bounds. That's totally fine. I'm just going to put it towards the end, but I should not write it here because these are my u's and 1 and 4 are my x bounds. So the integral of u is u to the 1/2 is u to the 3/2, so which makes it 2/3 because you divide it by something like this. Whenever you're dividing by a fraction, it's the same thing as multiplying by its reciprocal. U to the 3/2. But what is my u? My u is nothing but saying x to the 2/3 plus 1. Evaluated, now I put my x back, so I'm allowed to write 1 and 4. Another nice thing happens, these guys are gone, so I'm left out with nothing but saying this is the same thing as x to the 2/3 Okay, let's plug in our 4 here. So if we plug in our 4, so I would have 4 raised to the 2/3. You can use a calculator, or you can just do, because 4 squared is 16, so this would be cube root of 16, or you can break them down in furthermore, which is actually, I'll do it here, which is 2 cube root of 2 plus 1 raised to the 3/2 minus your lower bound. 1 raised to the anything is 1. 1 plus 1 is 2. 2 raised to the 3/2. So that is our final answer. Always leave it in exact form unless the question asked in decimal. All right, let's look at our next example. Find the arc length of y equals natural log of cosine of x from x equals 0 through x equals pi halves. Why don't you guys give it a try? Okay, so our setup would have looked like this. Remember, arc length formula involves the first derivative and then getting squared. So if we take the derivative of natural log of cosine of x, natural log of anything is 1 over the argument times, due to chain rule, the derivative of cosine is negative sine, and sine over cosine is tangent, so it's negative tangent. Then we also want to square the first derivative because the formula says so. So if we look at the derivation of the formula, it says the first derivative must be squared, right? So we're squaring the first derivative. So it becomes tangent squared. And I'm gonna just go ahead and plug in 1 plus tangent squared. The bounds are from 0 through pi fourths. I have no idea how to solve this problem, but that's where our Pythagorean identity is going to help us. Recall 1 plus tangent squared, or tangent squared plus 1, is nothing but saying this is the same thing with the help of Pythagorean. That's why we need to have our Pythagorean down. This is nothing but saying this is secant squared. And square root and the squared, that's even better, turns to just a secant x dx. And the integral of secant x, if you recall from your calc 1, it would be natural log of secant x plus tangent x evaluated from 0 through pi fourth. Plugging in the upper bound, you'd have natural log of secant pi fourths plus tangent of pi fourths minus upper bound minus our lower bound. So we would have natural log of secant of pi fourth would be 2 over square root of 2 plus tangent of pi fourth is 1 minus natural log of secant of 0 is 1 plus tangent of 0 is 0. So we would have left out with, let's leave it in exact form, 2 over root 2 plus 1. You can make it the same denominator, but this means minus natural log of 1, and natural log of 1 is nothing but 0. So if you simplify it inside the radical, you don't have to, we'll just leave the answer right here. This is our exact answer. Our next concept is surface area. So well, how the surface area works is the same kind of concept as when we talked about arc length, but remember, surface area is, we want to know if I revolve anything about any axis. For example, if I revolve this around here, we want to know how much area that was in the surface, not a volume. Volume would be in 3D, meaning also inside and so on, but only on the top outer surface. So let's just say if we did the same type of function that what we have, but if we cut down a little piece of this right here, in other words, this would look something like this. In other words, this right here is what we're calling the radius r, and this is what we're calling our change in length, which is what we are calling delta L. and we're revolving this around the x-axis. So you have something like this, something like this. Okay. So in other words, if I take out a little chunk, if I cut off a little piece in here that would look like a frustrum, and in other words, a frustrum would have two radius already. So this is R1, this is R2. How we calculated that radius R is basically taking the average of R1 and R2 by dividing by 2. So think about a big sausage you're chopping up into little pieces. So that one little piece, if I put it right here, that would have looked something like this. Also notice from a geometrical point of view or algebra point of view, you might have learned that the surface area is given by this formula, 2 pi RL, or I would write it out as what's going to happen if I write out 2 pi r times L. L is the same thing as saying length. And we actually, on our previous section, knew how to do length. So how is it going to change? What is R? If you look at this R right here, this R is nothing but the function F, right? So our surface area formula, it's going to develop as saying 2 pi integral from, let's say I call this point is A, and let's say this point is B. So we're calling integral from A through B of, instead of saying R, what is my R? This is my function f of x, square root of 1 plus f prime of x, that whole quantity getting squared dx. Why am I saying this? Notice this length, this should look familiar to you. So what it's really narrowing it down to, 2 pi r L. That is our formula. But we also derived what was L, so it just copies back here. So without doing any calculus, if I rewind it myself, this would have looked like 2 pi summation of f of x sub I, right? Because I'm taking smaller chunk, right? I'm taking all the summation of smaller of those disks right here, or the frustrums that makes a cross-sectional area. So that would have looked like 1 plus delta y sub I divided by delta x sub I, that quantity getting squared. And this is right here derived from, there was a delta x from our previous page. But our final formula narrows it down to this right here. Okay, let's look at an example how a surface area works. The integral can be modified, right? Because over here we have a and b. It could have been c and d, then it would be f of y, f prime of y, and this would have been dy. So find the area of the surface formed by revolving the graph of the function x squared. We know how the graph of x squared looks like pretty good. So let's write x and y. So we have x squared. We know it's a parabola, but let's see what region are we talking about, 0 through 1. So let's say 0 is here, let's say 1 is here. So it would be a parabola, but I only care about 0 through 1. It would have been something like this, but we don't really care about that. About the x-axis, so we're revolving about here, about the x-axis. So how's that going to look like? Roughly speaking, this would look like, this is the rotation, so it would look something like this. So you'd have another region, something like this. We are interested in finding all of this right here. Okay, so if I try to find out the surface area, I'm going to go ahead and basically use this formula, kind of like plug and chuck. So in order to do this, I need to know what is my first derivative. Well, that should be easy. F prime of x is 2x. So if I do my first derivative, that whole quantity getting squared, that would be 4x squared. Meaning I can say surface area equals 2 pi integral from the question says 0 through 1. So let's say this point right here is 1. So 0 through 1 square root of, let's just say, if I take, what is my f of x? My radius is, if I take a little chunk, that's my function. So what is my f of x here? It's nothing but x squared, that's my function, square root of 1 plus 4x squared dx. At this point, we do not know how to solve this, so I would leave the setup as how it is, but you should know how to put it on the calculator. Any basic TI-36 or a graphing calculator should be able to give you an answer. I always recommend getting an answer in terms of pi. So the answer, if you left it on your calculator, would be 1.21 pi. Please make sure you double check it because it might show up on the homework or on the exam. Like how would you, after you compute it, I would tell you to leave your answer in exact form in 2 decimal places in terms of pi. Because right as of now, we do not have the capability of how do you actually solve this. On chapter 8, we will learn techniques how to solve this type of intervals. Let's look at the same problem. And what I mean by same problem, here on the previous page, our function was y equals x squared. We revolved from 0, x equals 0 and 1. But the question on the previous page was revolved about the x-axis. Now things got a little changed. Now it's revolved about the y-axis. So how this is going to look like is same graph, 0 here, 1 here. You're not revolving about x anymore. Now we are revolving about the y-axis. So how's that going to look like? It's going to create another something like this. So in other words, we need to find out the surface area required on this guy right here. Okay, so same equation, same bounds. The questions revolution have changed. So in order to do this problem, I'm going to go ahead and do this problem 2 ways. One way might be tedious, but both ways are very important for you to understand and know. Notice, I'm not going to go ahead and do this. Well, first, you have to understand that we're not doing this problem in terms of dx anymore. Why? Because I'm not revolving about the x-axis anymore. The question asked us to revolve about y-axis. So let's go ahead and look at it. So I'm going to solve this in terms of dy. So if I solve this in terms of dy, the surface area would be 2 pi. Notice, if we solve it in terms of dy, formula gets changed. These are x bounds. Now, if we solve it in terms of dy, this becomes the y bounds, and the function have to be in terms of y, not in terms of f of x. So this is 2 pi. I need my y bounds. Well, if x is, so here's my function, f of x equals x squared. If x is 0, what is the y value? Well, I'll have 0 squared, which is just 0. Coincidentally, they happens to be the same, but this is my y value of 0. If x equals 1, what is the y value? Well, then you would have y equals 1 squared. Coincidentally, this becomes 1, and it doesn't have to be always 1. So this is also a y value of y equals 1. Okay, then it says f of x, that's the function. Now you'd have to have f of y. So if you know our parent function looks like y equals x squared, how do you solve for x? Well, I can take the square root, so I would have x equals plus and minus square root of y. But you can't have two functions going in as a radius, right? Because you're looking at something like this. So what I would recommend is think about this function. Where is, this is like this, and the other one is like this. To begin with, I don't know you recall or not, or I'll draw the picture. This really looks like this because we were doing from 0 through 1. This right here is the positive root. If the question asked for a negative, then I would have picked this guy. So to begin with, the question's bounds were given from 0 through 1. It wasn't given a negative, so I'm going to go ahead and pick this right here. I hope that makes sense. Because the graph, because of that plus and minus, you got a function got split up into 2. But originally the question's bounds were 0 through 1, which is on the right side. That's why we're taking the positive. So we would have square root of y, then square root of 1 plus the first derivative. So if I happen to take, so I'm not taking this guy. So if I take x equals square root of y is the same thing as y to the 1/2. So what would be dx dy? Not dy over dx, because now we're doing the problem in terms of dy. Well, this is nothing but saying 1/2 y to the negative 1/2. Okay, so let's go ahead and write that. Well, before I press to the cleaned up part, then it says the derivative should be squared. So it would be 1/4 y to the negative 1. Because if I square 1/2 y to the negative 1/2, if I square it, the square goes here, the square goes here. Okay, let's go ahead and write that out. 1/4 y to the negative 1/2. So here's my setup. Let's see how would we do this problem. In order to do this problem, you would have to do some kind of manipulation, or if you think about it, I have a square root, I have a square root. They're both square roots, so I'm allowed to write it as a 2 pi integral from 0 through 1. I can put everything under 1 square root. Y times 1 is y times 1/4, so y times 1/4 y to the positive 1, because negative 1 means 1. Positive 1 on the bottom, they can cancel out. So I would have really 1/4 dy. And you can only do such thing because they both have the same radical. Well, this is nothing, but this is also saying the same thing. What does square root means to us? Square root really means the same thing as saying a 1/2 exponent. So upon doing a u substitution, if I do my u as y plus 1/4, my du would be just 1 dy, because we're talking in terms of y. Notice I already have 1 dy. So the question really looks down at saying 2 pi. I'm not going to put my bounds because these are my bounds for y. I'm doing a u substitution. So this is like u to the 1/2 du. And how do we do those type of problem is u to the 3/2, 2/3. That makes it 4 pi thirds u. Our u is y plus 1/4 raised to the 3/2 evaluated from 0 through 1, because I back substituted my y's. Okay, let's plug in. So we would have 4 pi thirds. If I plug in 1 plus 1/4 is 5/4. So I would have 5/4 to the 3/2 minus, if I plug in 0, I would have 0 plus 1/4 is just 1/4. So I would have 1/4 raised to the 3/2. This is pretty much it, but I'm going to take it to one more level so that we get to actually see it on the problem I'm about to do in about 2 minutes. 5/4 raised to the 3/2. How can I write it? 5 is a prime number, so I can just leave 5 alone, saying 5 raised to the 3/2. But we can also write this as saying 4 raised to the 3/2. And 4 raised to the 3/2, this is nothing but, one can say 4 raised to the 1/2 and then a 3 and a cube. 4 raised to the 1/2 is 2, and 2 cubed is really nothing but 8. So this is really narrowing down this problem as saying 5 raised to the 3/2 over 8. So I can write 4/3 pi 5 raised to the 3/2 8 minus, notice this is 4, so this is also 4. So I would have 1 raised to the 3/2 is just a 1, but 4 raised to the 3/2, we said this is 8. I can also pull out a 1/8 from there, so it would look like 4/3 pi times 1/8, 5 raised to the 3/2 minus 1. Hence, I can cancel or simplify this, so I would have pi 6th 5 raised to the 3/2 minus 1. That's my exact answer, really clean version of it. Okay, so we did it in terms of y. A couple of things to remember when you're doing in terms of y, the function bounds needs to be in terms of y bounds. So this is what we did here. These are y bounds. The function got converted to f of y, not f of x. You have to look at it. Why is it f of y? Because the question was presented to us on the right side. That's why we took the positive. You don't look at dy over dx now. Once you convert it, you do dx over dy, and basically plug and chug, a lot of algebra involved. However, It's going to save us a tons of time. So I did this problem in terms of dy. So I'm going to redo the problem one more time, and you might really like it, this method. I'm going to call it in terms of dx. I'm going to solve it in terms of dx. Now you might be asking, why are you solving in terms of dx? But however, the question was presented to us in terms of actually dy, right? Because we were revolving about this axis. Well, here's a trick, and I will tell you in a second. So our function was y equals x squared. We need to know what's our dy dx because we're solving in terms of dx. So surface area formula still holds true. 2 pi integral. We don't have to worry about converting our bounds because we're setting up the problem in terms of dx now. Before it was in terms of dy. So that's why these are my x values, and the bounds of the question was presented to us 0 and 1. So 0 and 1, these are x bounds. What is my radius? Well, the radius is nothing but, if I draw something here, that's my function, which is x squared, square root of 1 plus the first derivative, dy over dx equals 2x. The first derivative getting squared would be 4x squared. Now, here's the trick. This right here is not x squared anymore. It's going to be the radius. It's going to be just a x. So be careful. Now you might be saying, why is it an x? Where am I getting an x? Think about it. From your Calc 1 or wherever you learn, do you remember or recall something called volume by cylindrical shells? If you don't, please Google volume by cylindrical shells. Whenever we are revolving about the y-axis, the distance that is covering here is any distance that is x units, unless you actually change the axis, like you're revolving about x equals 1, then you take the difference between those distances. I wouldn't make it that hard, but the trick is due to shell method. So if you don't know or you forgot how shell method works, please look up the idea of a shell method, how it works. That is why the radius is not the function anymore. When you're swapping things, it becomes x in here. So here's one of the tricks. dy, completely fine. Solve it, but make sure you swap out everything. If you still wanted to do a problem that is revolved about the y-axis, you can do it in terms of dx, but make sure you use that idea of a shell method. That's why it becomes easier. But if it was like previous problem, you cannot use the shell because it was already revolved about the x-axis. You can only use when you're revolving about the y-axis. So how is it going to look like? Let's see. This right here is going to be my u. So let's see if I do a u sub. My u is 1 plus 4x squared. My du is going to be 8x dx. I already have a 8x. I'm going to put an 8, provided I put a 1/8 outside. 2 and 1/8 makes it 1/4. So it becomes pi fourths integral of square root of u. And square root of u is nothing but saying u to the 1/2 du. How do you do that problem? That's super easy. U to the 3/2 with the 2/3 out in front, which makes life easier when we simplify. So this would be pi sixth. What is my u? 1 plus 4x squared raised to the 3/2, 0 through 1. Plug in your upper bounds. So you'd have pi sixth. 1 squared is 1, 4 times 1 is 4, plus 1 is 5 raised to the 3/2. If I plug in 0, 4 times 0 squared is 0, so I would have minus 1 raised to the 3/2. Ladies and gentlemen, let's take a look. This guy right here, and this right here, and this right here, same exact, well, 1 raised to the 3/2 is just a 1, right? So this right here and this right here are exactly the same answer. What's easier? It really depends on student to student. But if you have seen shell method, which you should have coming into calculus too, shell method really helps narrow down this problem. So I believe I attached some kind of picture that might help you doing this shell method. So if I scroll above, there might be some review. So towards the very end, after like the section work, you'd see review shell method. Here's basically that idea. How the shell method works is this is my circumference 2 pi r, so it becomes 2 pi x because you are unfolding it, that becomes a cylindrical shell like in 3D. So this distance that's becoming really an x, right? So that's why it becomes 2 pi. We said our formula was 2 pi the function, now it becomes r becomes our x, so that's why it's a 2 pi x height times dx, the thickness, right? So this guy is really a 2 pi x if you unwrap it. So recall from the shell method, if you haven't seen, I would just YouTube or Google some kind of videos that will talk about what in more details. That's a whole like chapter itself, but that's basically the idea. Shell method helps us to solve this problem much more efficiently. But if you do not remember shell method, not to worry, you can always solve this problem in terms of dy as well, but it might be a little complicated to do so. Okay, let's look at our next problem, some applications of surface area. So let R be the region given by this function 2 over 1 plus x squared. G is a parabola and x is a line. Write, but do not evaluate integrals representing each of the following. Find the total perimeter. Now, if you recall, perimeter is not a surface area, rather we're talking about arc length. So when we talk about arc length, we're talking about that L. So if you think about this, 2 over 1 plus x squared. So I'm going to go ahead and use, let's say this guy is my f. G of x, I'm going to use probably a green, so I'm going to sketch it so you get to see it. Okay, so let's see. So what the question, so we have a visual understanding what it's telling us. So here's our x-axis, here's our y-axis. F of x is 2 over 1 plus x squared. If I draw this, this would look something like, yeah, it's really going to look something like this, but we don't care about all of those regions. We only want to look at anywhere from here to here. I want to know what are these values. Well, I know this value is 2. Why is it 2? Because it's a line x equals 2. So here's that line x equals 2. G of x is a parabola. Well, my parabola would have gone something like this, or like this, but the intersection point is going to look like it's going to be something like this, right? What we are looking for letter A is the total perimeter. And when we say the word perimeter, just this, and this, right? So that region right there. So I'll write it out. G of x is my x squared. So this is right, my G of x. This purple one is my f of x. Okay, so we're gonna make a little easier probably. I'm gonna go ahead and call L1 as length of G of x. I'm gonna go ahead and call L2 as length of L2 is f of x, right? So anything in green, that's we're calling it L1. So this is L1. This guy right here, if I find the whole thing, I'm gonna call it L2. And I'm using what, black here. So L3, I'm gonna call it, what is L3, right? Well, I'm gonna call it the vertical distance from here to here, because that's literally that vertical distance, that's my L3. So I'll call it vertical distance. Okay, so how would you find L1? Let's get to the calculation. So in order to do L1, right? So the length of g of x, arc length formula. Arc length formula, recall, requires a derivative and the getting squared. So I'm going to go ahead and start with what's g prime of x. What is my g prime of x? It would be 2x. The g prime getting squared would be 4x squared. So L1 is nothing but saying the integral, some kind of bounds, right? So the bounds, the upper bound is going all, the green is going all the way to 2. So it's going to be 2 square root of 1 plus 4x squared dx. What is my lower bound? Okay, in order to do the lower bound, you probably have to think about how can I get this value where you see g of x and f of x, they both meets. In other words, from an algebra point of view, that's known as an intersection point. And if you find that intersection point, you can try it, just set these two equations equal to each other, you're going to get the value 1. Or you can see what value satisfy both the equation, and 1 would be that value. So that's why we're saying it's 1 through 2. L2. So that's my L1. We don't have to solve it. We're just going to talk about the setup. Right, you're not asked to evaluate. So L2, in order to do L2, what is L2? L2 is the same thing as saying length of the function f of x. So f of x looks like 2 times 1 plus x squared to the negative 1. I'm just writing it on the top so it's easier for us to do the derivative. So the derivative would be negative 2 1 plus x squared to the negative 2 times 2x, which indeed would look like, I'll write it here, which would look like negative 4x all over 1 plus x squared raised to the second. This is just f prime of x, but it requires f prime of x, that whole quantity, getting squared. So if I square all of this, this negative becomes a positive. 4 squared is 16x squared all over 1 plus x squared raised to the 4. Okay, so I'm gonna erase all of this work. So I'll go ahead and write f prime of x getting squared. We got 16x squared all over 1 plus x squared raised to the 4th. So let's see how's that gonna look like. So L2 is the purple one. Still, we're looking from 1 to 2. So I would have integral from 1 to 2 square root of 1 plus 16x squared all over 1 plus x squared raised to the 4 dx. That's my L2. Lastly, my L3. L3 is the vertical distance, so it's basically, what is L3? L3 is nothing but this height, right? Think about it. If I have something, let's say 7, and if I have something that is 1, how do you find the height? Is you say it's 6, because you subtract. The same concept over here. This height is g value evaluated at that point. What is that point? Its x value is 2. So it's g of 2 minus this height would be the value evaluated at 2 on the f function. So what is g of 2? G of 2 is 2 squared, which is 4, minus what is f of 2, which is 2/5. So the LCD is 5, so 20, so it would be 18/5. So that's my L3. So your final answer, the total perimeter, would be L1 plus L2 plus L3. So it would be then big integral 1 through 2 of root 1 plus 4x squared dx plus 1 through 2 square root of 1 plus 16x squared all over 1 plus x squared raised to the 4 dx plus 18/5. That would be your total area. You're not asked to solve this at this point. We do not know how to solve them, but you are asked to only do the setup, right? But do not evaluate. Letter B, find the area of the surface generated by revolving f, we're only revolving f from x equals 0 through x equals 1 about the x-axis. Setup only, you don't have to solve them. So we're revolving only f. So we actually did some hard work. We actually did the first derivative squared, that came out this. So when we're revolving this function now f about the x-axis, we're not revolving about y, so you should not be thinking about using shell method or any of those. How's the setup going to look like? It's talking about surface area of the surface. 2 pi integral from 0 through 1, right? Revolving about x means f of x goes outside, or the surface area formula, if I can show you to remind you. Right? This is our f of x because we're revolving about x-axis. So this right here would be f of x. What is our f of x? It's 2 over 1 plus x squared, square root of 1 plus 16x squared all over 1 plus x squared raised to the 4 dx. And that is our setup for the surface area. Where am I getting that? We already did all of this hard work here, so I just copy pasted that here. And this is really your f of x. This is your arc length. This is 2 pi RL. That concludes surface area as well, but these problems are taken from your homework and they're very probably challenging. So I will do one and I'll let you try one on your own. So let's go ahead and try this number 4. So, and what it's very required on this right here is algebra skills. It's not calculus, because it's asking us to do arc length, and I might put something similar like this on the exam. So when it's asking us to do arc length problems, what is really happening? Well, we know the arc length formula, right? In order to do our arc length formula, you need some bounds. It's given some bounds 1 through 3. So we can write arc length. We can do 1 through 3. Square root of 1 plus, we need the first derivative getting squared, dx. So let's go ahead and on the side calculate our first derivative. If y is this, dy over dx would be x to the 4. So the 4 comes out in front. So 4x to the cubed over 8, which becomes 1/2 x cubed. Okay, so let's go ahead and write it out. 1/2 x cubed. How would we take the derivative of 1/4 x squared on the bottom? I would have written something like this, x to the negative 2. So the negative 2 would have came out in front, x to the negative 3. So this would be negative 1/2 x to the positive 3 on the bottom. So that's your first derivative. Notice, if you do not get the first derivative right, everything's gonna go wrong after this. All right, so also it requires the first derivative must be squared. So that's where the problem lies. Before we were only used to seeing only one term. So if we would have just squared it, it was nice. But now you have two terms. So if I square this, this is literally gonna be a little tedious. Why? Because you got two terms. So you need to expand this binomial. Right? So we're gonna do some bunch of algebra and then we're gonna copy paste that over here. So let's do it on the side. So if I expand this, how's that expansion is gonna look like? Well, it would be nothing but saying, first, instead of doing all of this hard, crazy work, what if I factor out a 1/2? Then it would look like x cubed minus 1 over x cubed. And make sure you put that squared still there. Why am I doing that? Because I know 1/2 getting squared is just 1/4. I can easily do that. Okay, so this would be 1/4. How do we take care of x cubed minus 1 over x cubed? So if you recall, a minus b getting squared is a squared minus 2ab plus b squared. If you have a plus in here, then you get a plus in there. Or by all means, you can write it out twice, do your foiling and so on. What you're gonna end up getting in that is x to the 6 minus 2 plus 1 over x to the 6. If you don't get this, you should really write it out twice, do the foiling. This is what you should come down to. Okay, upon distributing the 1/4 now, how's that going to look like? Is 1/4 x to the 6 minus 1/2 plus 1/4 x to the 6. Right, so this is how it looks like. So I'm going to go ahead and copy this right here and put it in here. I'll use a blue. So if I do that, I would have 1/4 x to the 6 minus 1/2 plus 1/4 x to the 6, but it's on the bottom. Okay, looks like it's kind of like a good news here because we got like terms, and this is exactly why we're doing all of this. So this, what is happening? So this 1 and this negative 1/2 are my like terms. So we can do something. We can write square root of 1/4 x to the 6. 1 minus 1/2 is a positive 1/2 plus 1/4 x to the 6 on the bottom dx. Okay, once we write that, what else can we do? If you have a trinomial, you had 4 terms here. Now we added like terms, we turn it to a trinomial. I cannot do this integral. Now the question is, why can I not do this integral? I cannot do something like that, have all of this have a half exponent. So 1/4 x to the 6, 1/2 and 1/4 x to the 6. I cannot do it. No, you cannot just cancel, right? Why can't you cancel? Because this trinomial is raised to a half exponent. You cannot do this. Like, that's a big no. So please don't do that way. You cannot split up the exponent, right? You really need to know how to expand this using binomial expansion. That would be a nightmare. So here's that idea. We know from an algebra point of view, if I have a square root, if I can turn all of this work into a perfect squared, then I can cancel them. So our job is to somehow make all of this guy look like a perfect squared. If I can, then, and trust me, all of these problems we're going to handle, it's going to work out as a perfect squared. Okay, so we probably need another review how we can do that perfect squared. So recall from really algebra, if I have something given as, how did we learn how to factor x squared minus 6x plus 9? If you were given such thing, I don't know how you learned it, but you could have done something factoring, something like this, and you'd have said x, then minus 3, minus 3. Someone would have said x minus 3. Oh, that's pretty cool. Because if I had now said this was inside a radical, you couldn't have taken the integral of each individual term, but now after you factored it, well, then you could have canceled, and that's legal. Then you would have said this, and then you could have taken integral of each term. Right? So this is the same concept. How I like to see things, or I teach my algebra students, not like this factoring way that always works, but I would like to think about this. Is the first term a perfect squared? If so, what is that term? I always run that check first. That term is x. Is the last term a perfect squared? If so, what is that term? That's a 3. What is the sign in between? It's a minus. Let's take the product of them. 3 times x is 3x. If I double that, that becomes 6x. Did I erase it? Yeah. Why am I doubling it? Because the expansion have a 2 in there, right? So I'm basically, you always have to double it and see if that term is, so x times 3 is 3x. If we double it, that should always be there. If it's not there, no, you cannot use this. Right? Because the formula have a 2ab on the binomial expansion. So now I can really say, instead of doing all of this work, you can come down to here. So that's that review part. So let's check this over here. Is the first term a perfect squared? Well, you might think, 1/4 is a perfect square root of 1/2. So I'm going to go ahead and write 1/2. X cubed, I already said it, but how can we write x to the 6 as a perfect square? Probably a x cubed. The sign in between them is a plus sign. What is the last term? That would have been 1/2, also x cubed, but sitting on the bottom. And if I would only square it once I am sure, if I take the product of these two, that would be 1/4 x cubed, or I'll write it out steps. 1/2 x cubed times 1/2 x cubed here. They are gone, so I get 1/4. But remember, we always have to take the double because of that formula that have a 2 in there. So if I take double of that, they cancels out. I get 1/2. And check, I have 1/2 in there. So yes, bingo. Now I get to say this is nothing, but this is actually factors out. If you didn't like this method, you can try factoring this out. You should end up getting this. So bam, so these guys are gone. Now life is much easier. So you can really write as 1 through 3, 1/2 x cubed plus 1/2 x cubed dx. Without a radical, now what you can do is you can take the integral of each individual term, meaning what would be the integral of this? Integral, you add 1, you subtract, so that would look like, well, I wouldn't write 1 through 3 anymore, so it would be 4x to the 4 divided by 4, or x cubed is x to the 4 divided by 4. I have a 1/2, so it'd be 1/8 x to the 4. In order to do this, I cannot do it like that, so I have to write it as x to the -3. So -3 plus 1 divided by -3 plus 1. So it would be 1/2 x to the -2 all over -2. So this would be -1/4 x squared on the bottom. And my bounds are 1 through 3. Plug in the upper bound on both terms, plug in the lower bound on both terms, you should end up getting 92/9. Very, very, very important. If you want another practice, you may try doing this problem, y equals 1/2 e to the x plus e to the -x on intervals 0 through 2. Find the arc length of that. And if you did it correctly, you should end up getting approximately, if you put the answer on the calculator, the e value is 3.627, or the exact answer would be 1/2 e squared minus e to the -2. Please make sure you use that practice. And this is a homework problem for surface area and also some arc length problems. That concludes arc length and surface area.